All right, welcome back to the Chapter 1.3 video lecture slide series. And this was the last slide we went over, exercise in the brain. All right, so I'm going to give another question here. Researchers conducted a study on the effectiveness of a knee surgery to cure arthritis. It was randomly determined whether people got the surgery or not. Everyone who underwent the surgery reported feeling less pain. Is this evidence that the surgery causes a decrease in pain? Now, if this is all we knew, the answer is no. We would need a control or comparison group, such as what would happen without surgery. What if there's no surgery, but even though there's a randomization, it's a random experiment, it's not a randomized experiment because we didn't randomize the treatment variable. Okay, so what do we mean by control group? When determining whether treatment is effective, it is important to have a comparison group, usually known as the control group. It isn't enough to know that everyone in one group improved. We need to know whether they improved more than they would have improved without the surgery. All randomized experiments need either a control group or two different treatments to compare. So we need to do some type of a comparison. All right, so in the knee surgery study, those in the control group received a fake knee surgery. This is kind of nuts. So the control group in the study, there was a study that did a randomized comparative study where one group got the knee surgery and one group were put under and cut open, but the doctors did not actually perform the surgery. And what's crazy is all of these patients reported less pain. Those that got the surgery and those that got the fake surgery, put under and had a cut open on their knee. In fact, the improvement was indistinguishable between those receiving the real surgery and those receiving the fake surgery. All right, this is an example of the placebo effect. Here, I put a link here that talks about the placebo effect, where you just think something's going to happen and then it does. It doesn't actually, the treatment actually doesn't affect. It's more of you thinking there's a treatment. So the placebo effect says often people who will experience the effect they think they should be experiencing, even if they aren't actually receiving the treatment. One study done with pain, the classic example of this is the placebo is the sugar pill. So one group gets the pain treatment, and one group gets the sugar pill, and both groups said they feel better after a couple of hours, even the group that just got the sugar pill. And this is known as the placebo effect. One study estimates that up to 75% of the effectiveness of antidepressant medication is due to the placebo effect. Just the fact that people think they're getting medication that will prove something actually improves it, not the medication itself. And it's pretty nuts. If you think about it, I think the subconscious brain, the human brain, has a powerful effect. And there's another link I gave for the placebo prescription that goes into this study right here. All right, so one way to control for placebo is something called blinding. So a control group should be given a placebo. So in other words, you want to make sure the control group doesn't think they're not getting the treatment. So they're given a placebo, a fake treatment that resembles the active treatment as much as possible. Going back to the knee surgery, that's why in that study, the control group were put under and given a little slice on their knee to make them think they got the knee surgery. Because using a placebo is only helpful if participants do not know whether they are getting the placebo or the active treatment. And if possible, randomized experiments should be double-blinded. Neither the participants or the researchers involved should know which treatment the patients are actually getting. And this is important because you don't want the researchers, especially if they're being active with the control and experimental group, whether it's taking measurements, asking questions, doing tests, they don't want to know. It's good for the researchers not to know either, because there might be some subconscious or implicit bias or way that the researchers will let the groups know if they got the treatment or not. So there would be a third party that would know which group is which, but the researchers themselves would not know which group is the control in a double-blind study. Okay, so here's a good example of showing this. The study was conducted on 60 men with PIN lesions, some of which turned to prostate cancer. So these lesions often turn into prostate cancer. Half of these men were randomized, so 30 men were randomized to take 600 milligrams of green tea extract daily, and the other half were given a very similarly looking pill, but it was just a placebo pill, so it did not have green tea extract. The study was double-blind, so neither the participants nor the doctors who were working with the two groups knew who was actually receiving the green tea. So definitely, of course, there has to be a third party part of the researchers that knows which group is which, but the people that know which group is which will not be interacting with either group. After 1 year, only one person taking the green tea supplement got prostate cancer, while 9 of the 30 of the placebo group had gotten cancer. Later on this semester, we're going to be able to explain that this difference is unlikely due to just random chance. We're going to spend a lot of time on this first sentence in the rest of the semester, but just right now, assume a difference this large can't happen just by chance. Can we conclude that this provides strong evidence, so not absolute proof, we can't do that with statistics, but very strong evidence that green tea really does help prevent prostate cancer? In this case, the answer is yes. We have a randomized experiment that's double-blinded, and the treatment is randomized. The green tea extract, that was randomized. So we can draw conclusions about causality in this case. Okay, there's many types of randomized experiments. We're just going to focus on 2 in this class. If we randomize cases into different treatment groups, that is called a randomized comparative experiment. So the green tea example that we just went over, that is a randomized comparative experiment because there is 2 different groups. Which also used, maybe a little less common from what we've talked about, but is used fairly frequently, is called matched pairs. So that's the case where we give each treatment to each case. I think each case would be a person if we're talking about people. And we just randomize the order in which treatments are received. I'll go over an example here in a second to compare these 2. And either are valid randomized experiments. There are just times where matched pairs makes more sense than randomized comparative, and vice versa. Okay, so let's do an experiment to see whether people read faster on paper or a Kindle device. So a study was done in which 16 people read 2 sets of instructions of similar length, one on Kindle and one on paper, but the order of which they read the instructions was randomized. So the way I think about it, all 16 people read instructions on a Kindle and instructions on a paper, but half of those people read the Kindle first, then the paper, and 8 of the people read instructions on the paper first, then the Kindle. It turns out in this experiment that reading was faster on paper. What type of experiment is this? Right, this is an example of matched pairs. I think it's matched pairs because all participants in the study did both of the treatments, the paper reading and the Kindle reading. Go back. Matched pairs, each treatment to each case. We give each treatment to each case and randomize the order in which the treatments are received. So that's why this is matched pairs. Let's take the same question, speed of reading on paper versus Kindle. And a study was done with 16 people, same sample size. But in this case, suppose the sample was randomly split into 2 groups of 8 to read instructions. One group was given the Kindle, and the other group was given instructions on paper. And this experiment also, the reading was faster done on paper. This is an example of randomized comparative experiment. Because not everyone in the whole sample did both, you split up the sample into 2 groups, control group and treatment group, and compared those 2. Okay, I want to briefly go over why we don't always randomize. Of course, we should randomize. Those are ideal, but sometimes it's not ethical or possible. And often you have to do the best you can with data from observational studies. So example, does marijuana use affect memory? It's not ethical to randomly force people to use marijuana, or I suppose in many states now force people to not use marijuana. Another example is smoking. And one reason why the smoking debate lasted so long is the fact that you can't do a randomized experiment. It's unethical to take a group of people, randomly split them up, and force one group to smoke, say, a pack of cigarettes a day for 20 years, and one group to not smoke cigarettes for 20 years, and then compare their cancer rates. It's not possible to do ethically. So the the smoking and cancer debate had to be done with observational studies only. And it generally takes a lot more studies, and sometimes they're called meta-studies, studies of many studies, to then show that there's a causal association. So kind of a flowchart to think, was the sample randomly selected? Just the sample itself. This is going back to chapters 1 and 2. If yes, we could generalize to the population, or the population is. If the sample is not randomly selected, we should not generalize to the population. Then we're going to go a little bit deeper. Say, was the explanatory variable randomly signed? Think about that green tea example. The explanatory variable was the green tea, whether someone takes green tea or not. The response was the cancer rates. If it is randomly assigned, it's possible to make conclusions about causality. If it's not, we cannot make conclusions about causality. It doesn't mean it's bad. If we just have observational data, that's still good information to have. We can't go to that causality. All right, so 2 fundamental questions in data collection. One is kind of getting to this sample. Do we truly have a random sample? And in general, this is very, very, very difficult, especially when we're dealing with humans. And then the other one, if we're trying to get to causality, do we have a randomized experiment? All right, so the summary, doing a randomized experiment on a random sample is ideal, but rarely completely achievable. The focus of the study is using a sample to estimate a statistic for the entire population. You need a random sample, but you do not need a randomized experiment. If you think about election polling, you're just trying to figure out what percentage of people are going to go for candidate A versus candidate B in the upcoming election. We don't need an experiment. Observational studies are great for these, but you still need a random sample. If the focus of the study is establishing causality, something causes something else, then you need both a random sample and a randomized experiment. All right, so hopefully you can take away from this a couple things. Association does not imply causation. It can, but we can't assume. Association, correlation is very different than causation. Causation in general is much, 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 much more difficult to show than pure association. In observational studies, there's almost always confounding variables. So that's why we can't talk about causation directly from one observational study. Randomized experiments involve randomly determining the level of the explanatory variable. And randomized experiments prevent confounding variables. I would say can. They don't always do it completely, but they try to prevent these confounding variables. So we can talk about causality. The control or comparison group is almost always necessary. And the placebo effect exists, so placebo and blinding, and maybe possibly double blinding, should be used. And I'm going to finish this video lecture series with a comic. It's kind of a double layered comic. So hopefully that makes sense. And if it doesn't, keep thinking about it. I thank you for watching these videos.